Right now, somewhere beyond Neptune's orbit, an object from another star system is doing something that shouldn't be possible. Comet 3I Atlas just emerged from behind the Sun, glowing 7 times brighter than any comet we've ever tracked at that distance. 7 times. That's the difference between a candle and a searchlight. 3 NASA spacecraft watched it happen in real time, and every dataset confirms the same impossible number. And here's the thing that has scientists concerned. We have no idea why. The sequence of events began on October 21st, when 3I Atlas disappeared behind the Sun from Earth's perspective. For 6 days, the comet traveled through a region we cannot observe, a blind spot created by our star's brilliance. During those 6 days, something happened, something fundamental. On October 27th, the comet reached perihelion, and NASA's Stereo A, SOHO, and GOES 19 all locked their instruments onto it. What they recorded defied every model. The brightness curve was wrong. Its brightness was increasing at approximately 7 times the rate observed in typical Oort cloud comets. The researchers from Lowell Observatory and the U.S. Naval Research Laboratory wrote that the reason for the rapid brightening remains unclear. In scientific papers, that's as close as you get to saying, "We don't know what the hell is going on." The question everyone's asking, is this object actually a comet at all? Because here's what we're looking at. This isn't some random chunk of ice that wandered in from the Oort cloud. This is 3I Atlas, the 3I designation meaning it's the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017, which caused its own firestorm of controversy with its cigar shape and unexpected acceleration. The second was 2I Borisov in 2019, which behaved exactly like a normal comet and actually provided reassuring confirmation that comets from other star systems can be perfectly ordinary. But 3I Atlas is something else entirely. It doesn't orbit our sun. It's not gravitationally bound to our solar system. It came from somewhere out there, somewhere in the vast darkness between stars, and it's just passing through. Its trajectory is hyperbolic, which means it's moving too fast to be captured by the sun's gravity. It arrived, it's swinging around our star, and it will leave, continuing its journey through the galaxy to destinations we can only imagine. And during its brief visit, during those few precious weeks when we can actually observe it, it's doing things that challenge our fundamental understanding of what comets are and how they work. Let's back up to what happened before this moment, before the brightening anomaly, before the confusion. Let's talk about what 3I Atlas looked like when we first started paying attention. Early observations conducted months before perihelion, when the comet was still far from the sun, showed an object with a distinctly reddish hue. That coloration told a story. Red surfaces in space typically indicate organic compounds, complex carbon-based molecules that have been exposed to cosmic radiation for millions or billions of years. Think of it like rust on iron, except instead of oxygen reacting with metal, you have high-energy particles from stars and supernovae slowly altering the chemical composition of surface materials. Oumuamua had a similar reddish color, and so do many objects in the outer solar system, particularly in the Kuiper belt beyond Neptune. That reddish tint was actually reassuring. It suggested 3I Atlas was ancient, pristine, covered in materials that had been baking in the harsh environment of interstellar space for eons. It fit the profile. But then something changed. As the comet approached the sun and began to warm up, as volatile materials on its surface started to sublimate directly from ice to gas, the color shifted. By the time 3I Atlas emerged from behind the sun after perihelion, it wasn't reddish anymore. It was blue. Distinctly, unmistakably blue. That's a complete reversal, and it signals a fundamental transformation in the comet's activity. The blue glow isn't sunlight reflecting off a surface. It's emission, light being generated by specific molecules in the comet's atmosphere, in its coma, the vast cloud of gas and dust surrounding the nucleus. Scientists suspect the blue color comes primarily from diatomic carbon molecules, written as C2 in chemical notation. These molecules emit light at specific wavelengths in the blue part of the spectrum when they're excited by solar ultraviolet radiation. You might also have amino groups contributing to the color, NH2 molecules that also fluoresce blue. This isn't unusual in itself. Many comets show blue emission as they approach the sun. But the timing and intensity of the color change in 3I Atlas, combined with the extraordinary brightening rate, suggests something more complex is happening. The comet's chemical composition, or the way it's responding to solar heating, or both, differs significantly from what we consider normal. Here's where it gets interesting. The size of this thing. Ground-based observations before perihelion measured the coma of 3I Atlas, and the numbers are staggering. The fuzzy cloud surrounding the nucleus spans approximately half the angular width of the full moon as seen from Earth. Let me show you what that means. The full moon subtends about 0.5 degrees of arc in our sky. So we're talking about a coma, roughly 0.25 degrees across, maybe a bit more. But angular size depends on distance, and 3I Atlas was changing its distance from Earth dramatically as it swung around the sun. To get the actual physical size, you need to calculate based on the comet's position. When astronomers did that math, they found that 3I Atlas is enveloped in a coma stretching tens of thousands of miles in every direction. And then there's the plume. Observations detected a glowing extension, a tail or jet of material, reaching nearly 186,000 miles into space. That's about 3/4 of the distance from Earth to the Moon. Imagine something so massive it could almost bridge the gap between our planet and its natural satellite, and that's just the visible portion we can detect. The actual extent of the comet's influence on the surrounding space is the region where its particles and magnetic fields interact with the solar wind, could be far larger. Earlier observations conducted months before perihelion had detected a carbon dioxide halo around 3I Atlas with similar dimensions. Carbon dioxide, CO2, sublimates at relatively low temperatures compared to water ice. As the comet traveled inward from the outer solar system, CO2 was the first volatile compound to start vaporizing in significant quantities. That created the early halo. But as the comet got closer to the sun, as temperatures climbed higher, water ice began to sublimate as well. And that's when things really ramped up. Think about what that means for a moment. Water, H2O, is the dominant volatile in most comets. It's what makes up the bulk of their mass, the foundational material from which these objects formed in the cold outer regions of planetary systems. When water starts to sublimate in large quantities, you get a massive increase in the amount of gas flowing away from the nucleus, and that gas carries dust particles along with it, creating the spectacular tails and comas that make comets visible and beautiful. The transition from CO2-dominated activity to water-dominated activity usually follows a predictable pattern. We've observed it countless times, but 3I Atlas appears to have made this transition with unusual violence, unusual intensity. The radio observations that detected the sharp increase in water-related molecules tell part of this story. Radio telescopes can observe comets even when they're close to the sun, even when optical telescopes are blinded by glare, because radio waves aren't overwhelmed by solar brightness in the same way visible light is. The hydroxyl radical, OH, is a breakdown product of water molecules that have been split apart by solar ultraviolet radiation. It emits strongly at radio wavelengths. By measuring the intensity of OH emission, astronomers can estimate the rate at which the comet is producing water vapor. And for 3I Atlas, those measurements showed a dramatic spike as it approached perihelion. The comet was suddenly spewing water vapor at rates far higher than expected for an object of its estimated size. That's your smoking gun for the brightening anomaly. More gas means more dust entrained in that gas, and more dust means more surface area reflecting sunlight, which means higher brightness. But here's the problem. The increase is too steep, too fast. Even accounting for the water production rate, the brightening curve doesn't quite match the models. Something else is going on. Let's talk about what we do know. And trust me, what we know is already breaking every rule. When NASA's spacecraft captured 3I Atlas during its perihelion passage, they weren't just snapping pretty pictures. They were collecting precise photometric data, measurements of brightness at specific wavelengths over time. Stereo A, the Solar Terrestrial Relations Observatory spacecraft that's been orbiting the Sun since 2006, has a suite of instruments designed to study the solar corona and solar wind. But those same instruments can observe comets when they venture into the inner solar system. SOHO, the Solar and Heliospheric Observatory that's been stationed at the L1 Lagrange point between Earth and the Sun since 1995, carries coronagraphs that block out the Sun's disk to reveal the faint structures of the corona, and comets passing near the Sun show up brilliantly in those coronagraph images. GOES-19, the newest weather satellite in the Geostationary Operational Environmental Satellites series, launched specifically to monitor Earth's weather and space weather conditions, also carries a coronagraph, and it captured independent observations of 3I Atlas. 3 different spacecraft, 3 independent data sets, all telling the same story. The comet brightened at a rate approximately 7 times faster than typical Oort cloud comets. Let me put that in perspective. When a comet approaches the Sun, its brightness typically follows a power law relationship with distance. As the comet gets closer, it brightens according to a mathematical formula that involves the inverse of the distance raised to some power. For most comets, that power is somewhere between 2 and 4. If the power is 2, the brightness increases with the inverse square of the distance, doubling when the comet gets to half its original distance. If the power is 4, the effect is more dramatic. But whatever the specific value, the relationship is smooth and predictable. You can plot it on a graph, fit a curve to past observations, and forecast future brightness with reasonable accuracy. 3I Atlas broke that curve. The observed brightening significantly exceeded predictions based on standard cometary models. The researchers calculated that the rate was about 7 times higher than what you'd expect for a typical long-period comet from the Oort cloud at the same distance from the Sun. 7 times. That's not a subtle discrepancy. That's a fundamental mismatch between observation and theory. So what could cause this? One school of thought suggests it's related to the comet's composition. Maybe 3I Atlas is unusually rich in highly volatile compounds that sublimate explosively when heated. Carbon monoxide, CO, is a good candidate. It has a very low sublimation temperature, starting to vaporize when the comet is still far from the Sun. If the nucleus contains large deposits of CO ice that suddenly got exposed to solar heating as the comet rotated or as surface layers eroded away, you could get a sudden outburst, a spike in gas production that drives rapid brightening. There's precedent for this. Comet 29P Schwassmann-Wachmann is famous for its frequent outbursts, sudden brightenings caused by eruptions of CO-rich material from its nucleus. But 29P is a Jupiter family comet orbiting in the middle solar system, and its outbursts are sporadic, unpredictable. 3I Atlas showed a sustained brightening trend over days, not a single explosive event. That suggests something more systematic. Another possibility involves the structure of the nucleus itself. If the nucleus is unusually fragile, made of loosely bound material that crumbles easily under thermal stress, you could get continuous fragmentation as the comet approaches the Sun. Each time a chunk breaks off, it exposes fresh surface area, pristine ice that immediately starts sublimating, increasing the total gas production. More gas, more brightness. Fragmentation events have been observed in other comets, Comet Shoemaker Levy 9 famously broke into multiple pieces before colliding with Jupiter in 1994. Comet 73P Schwarzmann-Wachmann 3 split into dozens of fragments during its 1995 apparition. But those were catastrophic events, easily visible in telescopic images as multiple distinct nuclei. No such fragmentation has been detected in 3I Atlas. If fragmentation is driving the brightening, it must be happening on a smaller scale, continuous crumbling that creates rubble and dust, but doesn't completely shatter the nucleus. Another school suggests we're looking at this wrong. Maybe the issue isn't unusual composition or fragmentation. Maybe it's geometry. The way sunlight reflects off the dust particles in a comet's coma depends on the size and shape of those particles. If 3I Atlas is producing dust grains with a different size distribution than typical comets, grains that scatter sunlight more efficiently, you'd see enhanced brightness without necessarily requiring more total mass. Think of it like snow compared to water. A given mass of snow reflects far more light than the same mass of water because the snow is broken up into countless tiny crystals with enormous total surface area. If the comet is producing fluffy, highly reflective dust instead of compact grains that could explain the brightness anomaly, there's some evidence for this in the observations. The blue color of the coma indicates strong gas emission, but the overall brightness suggests significant dust as well. The ratio of dust to gas, the dust-to-gas ratio, is a key parameter in characterizing comets. Dust-rich comets look bright and diffuse. Gas-rich comets show strong emission lines but less continuum brightness. 3I Atlas appears to have both high gas production and high dust production, which could mean the nucleus is releasing material with an unusual mixture of dust and ice. But there's a third possibility, and this is where things get really strange. What if the brightening isn't caused by increased gas or dust production at all? What if it's an optical effect, something to do with the geometry of our observations? When we observe a comet, we're seeing light that has traveled from the sun to the comet, and then from the comet to our spacecraft or telescope. The brightness we measure depends on how efficiently the comet scatters sunlight in our direction. This depends on the phase angle, the angle between the sun, the comet, and the observer. At certain phase angles, particularly small ones, when we're looking at the comet with the sun almost directly behind us, there's a phenomenon called the opposition effect where brightness increases dramatically. But 3I Atlas wasn't observed at opposition. The spacecraft were viewing it from various angles as it passed the sun. Could there be some other geometric effect? Some peculiarity in how the dust scatters light at specific angles that's making the comet appear brighter than it should? It seems unlikely, but we can't rule it out without detailed modeling. For context, let's bring in the experts. Dr. Matthew Knight from the U.S. Naval Research Laboratory has been tracking 3I Atlas since its discovery, coordinating observations across multiple facilities and spacecraft. Knight has spent his career studying comets, particularly long-period comets and interstellar visitors. He was part of the team that observed 2I Borisov extensively during its 2019 passage, and he's keenly aware of how interstellar comets should behave based on that previous experience. 2I Borisov was textbook normal, a comet that looked and acted like thousands of comets from our own solar system. It had the right brightness, the right spectral properties, the right behavior as it approached and receded from the sun. That made it scientifically valuable as a comparison point, but also slightly disappointing to those hoping for something exotic. 3I Atlas is giving them the exotic. Knight and his colleagues are cautious in their published statements, emphasizing that they need more data to draw firm conclusions, but the undertone is clear. This object is puzzling. Dr. Teddy Carita from Lowell Observatory in Arizona has become one of the primary voices analyzing the photometric data. Lowell Observatory has a long, storied history in cometary science, going back to Clyde Tombaugh's discovery of Pluto in 1930 and continuing through decades of asteroid and comet surveys. The institution has access to excellent telescopes and a team experienced in extracting meaningful science from difficult observations. Carreta's work focuses on understanding the physical and chemical properties of small solar system bodies, particularly comets and asteroids, that blur the boundary between those two categories. He's seen unusual comets before, but the brightening rate of 3I Atlas stands out. In interviews and conference presentations, he's described the rapid brightness increase as one of the most significant anomalies they've encountered. The careful language he uses, the emphasis on needing more observations, reflects the scientific method at work, but also a genuine sense of uncertainty. They're not hiding data or spinning a narrative. They're genuinely trying to figure out what's going on. And then there's Dr. Avi Loeb from Harvard University, and his perspective adds a layer of provocative intrigue to the whole situation. Loeb is the Frank B. Baird Jr. Professor of Science at Harvard, former chair of the Astronomy Department, founding director of Harvard's Black Hole Initiative. He's a serious scientist with an impressive publication record and significant contributions to astrophysics. He's also become known, some would say notorious, for his willingness to consider unconventional explanations for astronomical phenomena. He was the most prominent scientific voice arguing that Oumuamua, the first confirmed interstellar object, might be an artificial probe rather than a natural asteroid or comet. That stance earned him both media attention and criticism from colleagues who felt he was straying too far from parsimony, the scientific principle that favors simpler explanations over complex ones. With 3I Atlas, Loeb is intrigued by the object's trajectory and the timing of its perihelion passage. He wrote that the comet's path through the inner solar system placed it in a geometrically unfavorable position for ground-based observation from Earth, hidden by the sun's glare at the most critical moment. But this same geometry was perfect for observation by NASA's space-based coronagraphs. He describes this as a possible hint of design. That word design is doing a lot of work there. On the surface, it seems like an odd statement. Why would the trajectory of a comet suggest design? Natural objects follow orbital paths, determined by gravity and the laws of physics. There's no designer choosing where comets go. But Loeb's implication, reading between the lines, is that if you were an intelligent civilization sending a probe into another star system, you might choose a trajectory that brings your probe close to the central star, where it can gather energy and data while remaining hidden from easy detection by any inhabitants on planets orbiting that star. It's a provocative idea, and most scientists push back hard against it. The consensus view is that 3I Atlas is a natural comet, nothing more, and that its unusual properties stem from composition or structure, not design. But Loeb's willingness to float these ideas keeps the conversation interesting, keeps people thinking about the boundaries of what's possible. Stop and consider that. We've now observed 3 confirmed interstellar objects: Oumuamua, 2I Borisov, and 3I Atlas. The first was bizarre, accelerating away from the sun without any visible cometary activity, shaped like nothing we'd ever seen, red and tumbling. The second was completely normal, a comet in every respect, boring and reassuring. The third is somewhere in between, clearly a comet with active gas and dust production, but behaving in ways that don't quite fit the models. What's the pattern? Are interstellar objects fundamentally different from solar system objects, or are we just seeing natural variation? The sample size is tiny, far too small for statistical conclusions, but every new data point matters enormously. Before Oumuamua, we had theories about interstellar objects, but 0 confirmed observations. Now we have 3, and each one is teaching us something new. The question everyone's asking: how many interstellar visitors are passing through the solar system at any given time? Statistical estimates based on the detection rate suggest there could be thousands or tens of thousands of such objects inside Neptune's orbit right now, most of them too small or too faint to detect with current technology. We're seeing the tip of an enormous iceberg. Every star system in the galaxy likely ejects some fraction of its comets and asteroids through gravitational interactions with planets or close stellar passages. Those ejected objects become interstellar wanderers, drifting through the galaxy for millions or billions of years. Some of them, by pure chance, pass through other star systems. A tiny fraction of those passages bring them close enough to our sun for us to detect. We're living in a cosmic shooting gallery, with debris from distant star systems constantly raining through our neighborhood. It's humbling and exhilarating, in equal measure. Now let's shift gears and talk about the technical challenges of observing 3I Atlas during perihelion. Ground-based telescopes couldn't do it. The sun is simply too bright. When you point a telescope at the sun, even from a slight angle, the scattered light inside the telescope overwhelms any faint objects nearby. It's like trying to see a firefly hovering next to a searchlight. The firefly might be glowing, but you'll never see it through the glare. That's why we need coronagraphs, specialized instruments that block out the sun's disk, using an occulting mask or disk positioned precisely in the optical path. With the sun blocked, you can see the much fainter corona, the sun's extended atmosphere, and any comets or other objects that happen to be passing through the field of view. NASA's SOHO spacecraft has been one of the most prolific comet discoverers in history, not because it's designed for comet hunting, but because its coronagraphs happen to be perfect for spotting sun-grazing comets, objects on trajectories that bring them extremely close to the sun. Thousands of small comets have been discovered in SOHO images, most of them members of the Kreutz family, a group of comets believed to be fragments of a single large comet that broke apart centuries or millennia ago. Those Kreutz sun-grazers rarely survive their perihelion passage. The intense solar heat vaporizes them completely, or tidal forces tear them apart. But 3I Atlas isn't a sun grazer. Its perihelion distance, the closest point to the sun, was far enough out that the comet wasn't in immediate danger of destruction. It was close enough for intense activity, but not close enough to die. That makes it a perfect target for study if you have the right instruments. Stereo A, the Solar Terrestrial Relations Observatory, added a crucial perspective. Stereo was originally two spacecraft, Stereo A and Stereo B, launched in 2006 to study the sun from different angles. The two spacecraft were placed in orbits that caused them to gradually drift away from Earth, one ahead of Earth in its orbit around the sun, one behind. This gave scientists stereoscopic views of solar eruptions and coronal mass ejections, three-dimensional information that's impossible to get from a single viewpoint. Stereo B was lost in 2016 after a mission anomaly during a solar conjunction, but Stereo A continues to operate. By now, it's drifted far enough around the sun that it observes from an angle substantially different from Earth's perspective. When 3I Atlas passed perihelion, Stereo A had a clear view from its position, capturing images and data that complemented SOHO's observations. The combination of multiple viewpoints is invaluable for understanding three-dimensional structures like a comet's coma and tail. And then there's GOES-19, the newest addition to NOAA's weather satellite fleet. GOES satellites normally watch Earth's weather, tracking hurricanes, monitoring atmospheric conditions, providing the data that goes into weather forecasts. But GOES-19 carries a solar ultraviolet imager and a coronagraph as part of its space weather monitoring package. Solar storms, coronal mass ejections, can affect Earth's magnetosphere and cause disruptions to satellites, power grids, and communications. Monitoring the sun's corona helps predict these events. The coronagraph on GOES-19 gave yet another independent view of 3I Atlas, and the fact that a weather satellite happened to be in the right place at the right time to observe an interstellar comet is one of those happy accidents that sometimes occur in science. But there's another observation technique that proved crucial: radio astronomy. While the sun's visible light overwhelms optical telescopes, radio telescopes can observe right through the glare. Radio waves aren't scattered or absorbed by the bright solar disk in the same way. You can point a radio telescope at a comet that's angularly close to the sun and get clean data. The hydroxyl radical, OH, emits at a wavelength of 18 centimeters, right in the radio spectrum. This emission is one of the primary ways we detect water in comets, because water molecules are broken down by solar ultraviolet radiation into OH and hydrogen. The OH emission is proportional to the water production rate. Measure the intensity of the OH line, apply some known conversion factors, and you can calculate how many water molecules per second are streaming off the comet's nucleus. For 3I Atlas, those measurements showed a dramatic increase as it approached perihelion. The comet was producing water vapor at rates in the range of billions of kilograms per day. Billions of kilograms per day. That's about the mass of a small office building worth of water being vaporized every 24 hours. And this is just the water. There's also carbon dioxide, carbon monoxide, methane, ammonia, and other volatiles sublimating from the surface. The total mass loss rate could be significantly higher. Over the course of days or weeks, near perihelion, a comet can lose a substantial fraction of its total mass. If the nucleus is only a few kilometers across, which seems likely for 3I Atlas based on brightness estimates, it might have a mass on the order of trillions of kilograms. Losing billions of kilograms per day is sustainable for weeks, maybe months, but not indefinitely. Eventually, the comet will exhaust its most volatile materials, and the activity will decline. Here's another piece of the puzzle that deserves attention. The shift from red to blue in the comet's appearance isn't just aesthetically interesting. It tells us about the chemical evolution of the coma as the comet warmed up. Early on, when the comet was far from the sun and relatively cold, the surface had a reddish color from organic compounds, but there wasn't much active sublimation. The coma was tenuous, mostly just small particles of dust ejected by trace amounts of gas. As the comet moved inward and temperatures rose, carbon dioxide started to sublimate in significant quantities. CO2 doesn't contribute much to visible color, but it drives dust production and begins to create a more substantial coma. Then, closer to the sun, water ice started to sublimate, and that's when you get the blue color from C2 and other molecules. The sequence of colors and the intensity of emission lines are like a chemical signature, a fingerprint that tells you what the comet is made of and how it's responding to solar heating. Spectroscopy, the technique of splitting light into its component wavelengths, would reveal detailed information about the molecules present in the coma. Every molecule has a unique set of emission or absorption lines, specific wavelengths where it interacts with light. By taking a spectrum of 3I Atlas and analyzing the lines, you can identify the molecules and even estimate their abundances. Unfortunately, spectroscopy of comets close to the sun is challenging for the same reason imaging is: the glare. But as the comet moves away from the sun in November and December, as it becomes visible in twilight and night skies from Earth, ground-based telescopes will be able to target it with spectrographs and gather that crucial data. Speculation time. Let me walk you through one possible scenario for what's happening inside the nucleus of 3I Atlas. Imagine the nucleus is a loose conglomeration of ice and dust, a rubble pile held together by weak gravity and the cohesion of ice. This structure formed billions of years ago in the protoplanetary disk of another star. A star we'll never identify because we can't trace the comet's trajectory back far enough through the galaxy. For billions of years, this object drifted through interstellar space, cold and inert, with surface temperatures only a few degrees above absolute zero. Cosmic rays and interstellar particles slowly altered the surface chemistry, creating the reddish organic compounds we saw in early observations. Then, maybe a few million years ago, a gravitational interaction with a passing star or a chance encounter with a giant molecular cloud altered the comet's trajectory, sending it on a path that would eventually intersect our solar system. As it approached the sun, the outer layers began to warm. First, CO2 ice started to sublimate, creating internal pressure. Gas percolating up through the porous nucleus carried dust particles to the surface, where they were ejected into space. This early activity created the carbon dioxide halo. As the comet got closer and warmed further, water ice started to sublimate. Water releases far more gas than CO2 for the same amount of heating because it's more abundant and has a high latent heat of sublimation. The sudden increase in gas production fractured the fragile nucleus, breaking off chunks and exposing fresh ice. This triggered a runaway process. More exposed ice means more gas, which carries away more dust, which exposes even more ice. The result is the explosive brightening we observed. The blue color comes from carbon molecules, formed by the breakdown of organic compounds in the intense ultraviolet radiation close to the sun. As the comet recedes from perihelion, the process will gradually reverse. Temperatures will drop, sublimation will slow, and the brightness will decline. But the comet has been fundamentally altered by its encounter with our sun. It's lost mass, changed shape, exposed inner layers that haven't seen sunlight in eons. That's one scenario. Here's another. Maybe the nucleus isn't a rubble pile. Maybe it's a solid block of ice. More like a dirty iceberg than a loosely bound aggregate. If the ice has different compositions at different depths, layers with varying amounts of CO2, CO, and other volatiles embedded in a water ice matrix, you could get sequential outbursts as each layer is exposed. The surface starts off rich in CO2 because CO2 has a lower sublimation temperature and has been slowly escaping over the long journey through interstellar space, creating a CO2-enriched outer shell. As this shell sublimates away near perihelion, it reveals deeper layers that are water-rich. The transition from one layer to the next causes a sudden change in gas production rate, which drives the rapid brightening. This layered structure could be a result of the comet's formation process. If it formed in a protoplanetary disk that was cooling down over time, or in a region where the temperature gradient was steep, different layers might have condensed under different conditions, locking in different compositions. Or maybe the layering developed later, during the long interstellar journey, as cosmic ray irradiation gradually altered the surface while leaving the interior pristine. Either way, the key insight is that the nucleus might have a complex internal structure that's only revealed when solar heating drills down through the layers. But let's bring this back to the controversial angle. Now, before you dismiss this as fringe science, consider the words of Avi Loeb again. When he describes the trajectory of 3I Atlas as showing a possible hint of design, he's not necessarily suggesting little green men built the comet. He's pointing out that the object's path through the solar system is, from a certain perspective, fortuitous for scientific study. It arrived at a time when we have multiple spacecraft with coronagraphs in position to observe it. It passed behind the sun at an angle that made it visible to those spacecraft. If the trajectory had been slightly different, we might have missed it entirely, or we might have only caught glimpses insufficient for detailed analysis. Loeb's broader point, which he's made in numerous interviews and papers, is that we should be open to the possibility that some interstellar objects might be artificial, and we shouldn't dismiss that hypothesis out of hand, just because it sounds like science fiction. The reasoning goes like this. If technological civilizations are common in the galaxy, and if such civilizations develop space exploration capabilities, they might send probes to other star systems, just as we've sent Voyager 1 and 2 out of our solar system. Some of these probes might be defunct, dead relics from civilizations that no longer exist, or no longer maintain their ancient missions. These dead probes would appear to us as inert objects tumbling through space, distinguishable from natural asteroids or comets only by subtle anomalies in their properties or behavior. Oumuamua's unusual acceleration, unexplained by visible cometary activity, was what caught Loeb's attention. He co-authored a paper suggesting that the acceleration could be explained if Oumuamua were a light sail, a thin reflective sheet pushed by solar radiation pressure. Most astronomers found this explanation unconvincing, preferring models where the acceleration was caused by outgassing of volatiles that didn't produce visible dust, making Oumuamua a comet despite the lack of a tail. But Loeb's point remains valid. We should look at the data and consider all possibilities. With 3I Atlas, there's no need to invoke artificial origins. It's clearly a comet, showing all the hallmarks of natural cometary activity. The gas, the dust, the brightening, all of it can be explained by sublimation of ice. But the intensity of the brightening, the color change, the sheer scale of the coma, all of it is unusual enough to warrant careful study. Most scientists push back hard against the idea that we should spend time considering artificial explanations for every anomalous object. The reasoning is pragmatic. We have limited telescope time, limited resources, limited personnel. If we chase every strange observation with speculation about aliens, we'll waste time that could be better spent doing conventional science. Moreover, there's a principle called Occam's razor, the idea that simpler explanations are generally better than complex ones. If you can explain an observation with known physics and chemistry, you shouldn't invoke unknown or speculative mechanisms. Natural comets are known. We've observed thousands of them. We understand the basic processes, even if the details sometimes surprise us. Artificial probes from alien civilizations are speculative. We have no confirmed examples, no clear signatures for how to identify them. Given that, it makes sense to exhaust natural explanations before considering artificial ones. But Loeb argues that this approach has a blind spot. If we're not looking for signs of technology, if we automatically assume every object is natural, we might miss evidence, even if it's right in front of us. It's a philosophical debate as much as a scientific one, and it's unlikely to be resolved soon. But it keeps the conversation dynamic, keeps researchers thinking critically about assumptions and biases. The next critical window is November through December 2025, when 3I Atlas will be visible in twilight and night skies, moving away from the sun and becoming accessible to ground-based telescopes. This is when the real science will happen. Spacecraft observations during perihelion were invaluable, but they had limitations. Coronagraphs are designed for broad-field imaging, not detailed spectroscopy. They can tell you how bright the comet is and give you a rough sense of its color, but they can't provide the high-resolution spectroscopic data needed to identify specific molecules and measure their abundances precisely. Ground-based telescopes, particularly large research telescopes with sensitive spectrographs, can do that. Astronomers worldwide are already scheduling observing time, preparing instrument configurations, coordinating campaigns to maximize coverage. They want to catch the comet while it's still relatively bright and active before it moves too far from the sun and fades into obscurity. The observations will focus on several key questions. First, what is the detailed chemical composition of the coma? Which molecules are present and in what ratios? This will tell us about the composition of the nucleus and how it compares to comets from our own solar system. Second, how does the brightness evolve in the weeks after perihelion? Does the rapid brightening continue, or does it level off and decline? This will help constrain models of the comet's activity. Third, is there any evidence of fragmentation or jets? High-resolution images might reveal structure in the coma, asymmetries that indicate localized sources of gas and dust on the nucleus. Finally, can we determine the size and rotation period of the nucleus? This requires careful photometric monitoring over time, looking for periodic variations in brightness as the nucleus rotates and presents different faces to the sun. Let me shift gears and talk about what this means for the bigger picture, for our understanding of the galaxy and our place in it. Every interstellar object we detect is a messenger from another star system, carrying information about conditions in a distant planetary system at some point in the past. When 3I Atlas formed, billions of years ago, it condensed from gas and dust in the protoplanetary disk of a star we'll never see. The chemical composition of that disk, the mixture of elements and compounds, was determined by the history of that region of the galaxy, by the generations of stars that lived and died before the comet's parent star was born, by the supernova that enriched the interstellar medium with heavy elements, by the processes that created complex organic molecules in cold molecular clouds. All of that information is encoded in the comet's composition. By studying 3I Atlas, we're studying the chemistry of another planetary system, comparing it to our own, learning whether the processes that led to the formation of our solar system are universal or whether there's significant variation. Early results from 2I Borisov suggested that interstellar comets aren't fundamentally different from solar system comets, which was reassuring, but also slightly disappointing. If all comets are the same, it means the processes of planetary system formation are highly uniform, which is scientifically valuable, but limits the diversity of what's out there. 3I Atlas, with its anomalous behavior, hints that maybe there's more variation than we thought. Maybe different star systems produce comets with different properties, different compositions, different structures. That would make the galaxy a more interesting place. Think about what that means for the search for life beyond Earth. Life as we know it requires water, organic molecules, and energy. Comets deliver all three. They're made largely of water ice, they contain organic compounds, and they release energy when they impact planets, driving chemical reactions. There's a hypothesis that Earth's oceans were at least partially delivered by comets in the early solar system, during a period called the Late Heavy Bombardment, when the inner planets were pelted by asteroids and comets. If comets played a role in making Earth habitable, then understanding cometary composition and diversity is directly relevant to understanding the potential for life elsewhere. Interstellar comets add another layer to this. If comets can travel between star systems, they could potentially transfer organic molecules or even microbial life from one system to another, a process called panspermia. It's a speculative idea, and most scientists are skeptical that life could survive the harsh environment of interstellar space for millions of years, but it's not impossible. Microbes have been shown to survive in space for extended periods, protected by rock or ice. If panspermia occurs even rarely, it would mean that life in the galaxy might have common origins, related not by common descent from a single planet, but by physical transfer of organisms between worlds. Studying interstellar comets like 3I Atlas gives us a window into these processes. Actually, let me correct that. The idea that Earth's oceans came primarily from comets has fallen out of favor in recent years. Isotopic measurements of water in comets show that most comets have a higher ratio of deuterium to hydrogen, DH, compared to Earth's oceans. Deuterium is heavy hydrogen, an isotope with an extra neutron. The DH ratio is like a fingerprint that tells you where water formed. Comets from the Oort cloud tend to have DH ratios about twice as high as Earth's oceans, which suggests they formed in a colder, more distant part of the solar system. Asteroids, particularly carbonaceous chondrites from the outer asteroid belt, have DH ratios much closer to Earth's oceans. So the current thinking is that most of Earth's water came from asteroids, not comets. But comets still delivered some water, and more importantly, they delivered organic molecules. Comets are rich in complex carbon compounds, the building blocks of life. When comets impact a planet, they deliver these compounds to the surface, seeding the planet with prebiotic chemistry. That's valuable regardless of whether the comets also delivered the water. And the fact remains that if you want to understand the inventory of water and organics in the galaxy, you need to study comets, including interstellar comets. Here's where things get really strange. Let's talk about the possibility, however remote, that 3I Atlas is not entirely natural. I'm not suggesting it's an alien spaceship, but what if it's a natural comet that was modified, deliberately or incidentally, by a technological civilization? What if it's a comet that passed through another star system where an advanced civilization was conducting mining operations or industrial activities, and some of the material from those activities contaminated the comet, altering its composition? This is wildly speculative, bordering on science fiction. But bear with me. If you were a spacefaring civilization extracting resources from asteroids or comets in your own system, you'd inevitably create debris, tailings from mining operations, exhaust from propulsion systems, industrial byproducts. Some of that material would end up drifting through space, and some of it might encounter interstellar objects passing through your system. If one of those interstellar objects then continues on its way and eventually enters another star system, it might carry trace contaminants from your civilization. Detecting such contaminants would require extremely sensitive measurements, looking for elements or isotopes that don't occur naturally, or that occur in ratios inconsistent with natural processes. There's no evidence that 3I Atlas has any such contaminants. The observations so far are consistent with a natural comet, but we haven't done a detailed elemental analysis. We haven't measured isotope ratios for multiple elements. As the comet becomes accessible to ground-based telescopes in November and December, if astronomers can get high-resolution spectra, they might be able to look for anomalies. It's a long shot, but it's the kind of thing that, if you found it, would be earth-shattering. And here's what they don't say in the papers, not explicitly anyway. There's a tension in the scientific community about how aggressively to search for signs of extraterrestrial technology. On one hand, the discovery of alien technology, even ancient and defunct technology, would be the most important scientific discovery in history. It would answer the question of whether we're alone in the universe, and it would provide information about what advanced civilizations do, how they explore, what technologies they use. On the other hand, the search for extraterrestrial intelligence, SETI, has been going on for decades with no confirmed detections. The null result, the absence of clear signals, has led some scientists to conclude that technological civilizations are extremely rare, or that they don't broadcast or build detectable megastructures, or that we're looking in the wrong ways. In this climate, proposing that we should examine every anomalous asteroid or comet for signs of technology feels to some like a waste of resources, a distraction from productive science. But to others, it feels like a question too important to ignore. Loeb's position is that we should at least look. We should take the data we're already collecting and analyze it with an open mind, considering all possibilities. If an object shows clear signs of being natural, fine, move on. But if an object shows anomalies that can't be easily explained, we should investigate further before dismissing it. It's a reasonable position, even if most researchers don't share his enthusiasm for considering artificial explanations. You have to read between the lines in the scientific literature to see these debates. Papers are written in cautious, technical language that avoids speculation and focuses on data. But in conferences, in hallway conversations, in emails between colleagues, the discussions are more open, more wide-ranging. Scientists are humans, and they're curious about the big questions: the existence of life and intelligence beyond Earth, the future of humanity in the cosmos, the ultimate fate of the universe. These questions motivate a lot of research, even if they're not stated explicitly in grant proposals or journal articles. Studying an interstellar comet like 3I Atlas is, on the surface, about understanding cometary science, planetary formation, the dynamics of the galaxy. But underneath, it's also about the question of what else is out there. Who else might be looking at the stars, wondering if they're alone? Let's bring this back to the immediate mystery. Why is 3I Atlas brightening so rapidly? We've explored several possibilities: unusual composition with high volatile content, continuous fragmentation exposing fresh ice, geometric effects related to dust scattering, layered structure with sequential outbursts. Each of these mechanisms could contribute to the observed brightening. It's likely that the real explanation involves a combination of factors. Comets are complex, heterogeneous objects, and their behavior is influenced by many variables. The detailed composition of the nucleus, its structure and porosity, its rotation state, the history of its thermal evolution. No two comets are exactly alike, and every comet we study adds to our understanding of the range of possible behaviors. 3I Atlas is on the extreme end of that range, which is why it's so interesting. The observations planned for November and December will be crucial. If astronomers can measure the rotation period, they might find that the comet is rotating unusually fast or slow, which would affect how gas is released and how the coma forms. If they can detect specific emission lines from molecules like CN, C2, C3, NH2, and others, they can compare the ratios of these species to ratios in solar system comets, looking for similarities or differences. If they can measure the dust-to-gas ratio and the size distribution of dust particles, they can build better models of the comet's activity. All of this data will feed into computational models, simulations that try to reproduce the observed properties by adjusting parameters like composition, structure, and activity patterns. Eventually, the models will converge on a self-consistent picture of what 3I Atlas is and why it behaved the way it did. But there will always be uncertainty. Comets are observed from a distance, sometimes a very large distance, and we can only infer their properties from the light they emit or reflect. We can't land on them, we can't drill into them, we can't analyze samples in a laboratory. Well, we have done that for a few comets. The Stardust mission returned samples from Comet Wild 2 in 2006. The Rosetta mission orbited Comet 67P Churyumov-Gerasimenko for 2 years and deployed a lander, Philae, onto its surface. These missions provided invaluable data, but they also showed just how complex and surprising comets can be. 67P turned out to have a bizarre shape, like two lobes stuck together, a rubber duck profile that raised questions about its formation. The surface was far more varied than expected, with smooth plains, rugged cliffs, jets of gas and dust erupting from specific locations. The composition included organic molecules far more complex than anticipated. Every mission to a comet reveals surprises, and we've only studied a handful up close. 3I Atlas won't get a dedicated spacecraft mission. It's moving too fast, and we didn't have enough warning to design, build, and launch a probe to intercept it. We're stuck with remote observations. But those observations, if done well, can still reveal a great deal. The bright blue coma of 3I Atlas comes from C2 fluorescence. UV sunlight excites diatomic carbon molecules, which then emit blue-green light as they relax. The strength of this emission depends on both the amount of C2 and the UV intensity. C2 itself is produced when CO2, CO, and organic molecules break apart near the sun, so comparing C2 with CN and OH emissions helps astronomers determine the comet's chemical makeup and its place in comet compositional taxonomy. This chemistry reflects the environment in the comet's birth system. The rapid brightening shows the coma wasn't in steady equilibrium. The comet was producing gas and dust faster than the coma could expand and stabilize, revealing time-dependent dynamic activity. The coma's huge size, tens of thousands of miles across, visible as half the moon's apparent diameter, indicates a very high gas production rate and strong forces shaping the dust, including radiation pressure forming the tail. The faster or slower ejection speeds influence whether the coma is more compact or widely spread. Scientists with preliminary spacecraft data haven't released details yet, waiting for peer review, but early hints say the brightening rate is about 7 times faster than average comets. Still, that number has uncertainties. How wide are the error bars? And what exactly counts as typical? Since Oort cloud comets show a huge variety of behaviors, detailed analysis will determine whether 3I Atlas is truly an extreme outlier or simply on the fast end of a broad distribution, helping clarify what makes this interstellar comet unique. Interstellar Comet 3I Atlas gives us a rare chance to study material from another star system. Its perihelion distance determines how hot it becomes near the Sun, which in turn controls what ices sublimate. Carbon dioxide activates at around 150 Kl far from the Sun, while water only becomes dominant above about 200 Ki much closer in. The level of heating will show whether its activity comes mainly from water or more volatile ices. The discovery of interstellar objects is recent, enabled by advanced sky surveys like Pan-STARRS. We expected to find maybe one such object per year, but in less than a decade we've already found 3. The first, Oumuamua, was bizarre. No coma, odd shape, unexplained acceleration. The second, 2I Borisov, acted like a normal comet, proving that some interstellar visitors are familiar in behavior and composition. 3I Atlas is different again, brightening much faster than models predict, and presenting a new scientific puzzle. These objects show the solar system is part of a larger galactic network, where matter drifts from one star system to another. 3I Atlas, likely formed billions of years ago from the debris of an ancient star, became part of a young planetary system, was ejected, and wandered the galaxy until it crossed our path by chance. Studying it helps with practical concerns like predicting comet activity for planetary defense, and it informs models of planet formation and chemical diversity across the galaxy. As it approaches the Sun, astronomers and skilled amateurs will gather data through spectroscopy, photometry, and imaging, trying to understand its rapid brightening and internal structure. Eventually, the comet will fade back into the interstellar dark, but its data will influence research for years. The mystery may not be completely solved, but anomalies like this push science forward, forcing us to rethink assumptions. 3I Atlas reminds us that the universe still surprises us, that we are part of a vast cosmic environment, and that our curiosity, our drive to observe, question, and understand connects us to that larger story.